Um, and that being said, I want to take this opportunity now to talk to you about Python and why we care about Python. I picked up this logo for the Python scale. So like I mentioned, for the Python snake. So I mentioned last time briefly about this IEEE Spectrum magazine and how important Python is. So these data I collected from programming language rankings in 2019. I haven't updated the stack yet, but I have no doubt it is identical. And ranking programming languages with most job postings or with most ability based on scientific computing, web development, and user interface, user flexibility. Python ranks #1. And if you change the statistics, the conditions a little bit, you see on the lower left over here, there is Java comes top, and then Python, because I changed a little bit the conditions on the metric of what you can do. But then look at MATLAB ranking at #8. It can just barely do a few things. You can barely do a few things with MATLAB, pretty much focused on scientific computing. I don't have anything against MATLAB, so don't get me wrong. I used to program in MATLAB. I used to program in Fortran. These are all just languages, that I know, but I like to be up to date with the latest and greatest, okay? Now, why Python? Again, because there's a lot of Python in your future, at least for the next decade. It will be replaced by another language, so there's no doubt about that. And Python is free. I mentioned that last time. It's very easy to get started with Python. Python is very forgiving. I gave the example, you add an apple and orange and you get a watermelon and it just works, I really like that about Python. And most of the things you do, would not be allowed in a language, in a strongly typed language like C or C++, for example, or even MATLAB. But Python is very flexible, allows you to add like a constant to an array, for example. In C++, you can't do that because those are different types. Okay, and there's a significant community support around Python. You pretty much every other person you've met probably knows Python. That would be actually an interesting experiment to do. Ask someone you meet, like, hey, do you know Python? And just count the number of people whom you meet who know Python. And you can use Python in a web browser, and that's kind of what I'm going to try to promote here today, and to kind of encourage you to adopt as you move on towards your future. This is the symbol of a planet. What is it called? Do you know? What's a planet that has the big red spot and giant storm in it, a raging storm? Jupiter, right? Yeah. So, but here we're gonna spell Jupiter a little bit differently with a Y instead with an I. There's this thing called the Jupyter Notebook. You might have heard of it or not, but now you're hearing of it. And I want to just dispel the myth around it, remove any confusion about it. Jupyter Notebook is just a web application that allows you, it's a web application, has nothing to do with Python, okay? It has nothing to do with Python. It's a web application that allows you to write code. This code could be Python, could be Fortran, could be C++, could be R, could be whatever, okay? It allows you to write equations. That's great. Allows you to put in visualizations, like import pictures and graphics, and it allows you to add explanatory text. So Jupyter has nothing to do with Python. In fact, it supports over 40 languages. Python is just one of them. However, when you hear Jupyter Notebook, you immediately think you're doing Python because Python is just so popular. And the idea of the Jupyter Notebook grew around Python. Now, I'll show you in a few minutes what a Jupyter Notebook looks like. It's just a blank thing. You start typing in it. You can type code, you can type text, and the sky is the limit what you can do with it. You can write great reports in it. But the best part is that it's all inclusive of everything you need to do. You can just do it in one place. And that's why we like to promote it. The challenge, however, is that you must use it locally. Now, for a first-time programmer, which typically is the kind of student I get in this class, or for someone using Python for the first time, and me personally, the last thing I want to do is download something, install it, and figure out all the dependencies that I need to deal with. I don't care about that. This should be a software that should be smart. It should install itself and do everything. I just want to work with the application itself. I don't want to worry about installing things and getting licenses and any of that. And so it turns out that you know, that's one of the challenges of adopting Python, but of adopting the Jupyter Notebook. But we can make this even easier. There's this thing called Jupyter Hub, which essentially puts the notebook on a server. Okay, it puts the entire application of the Jupyter Notebook, instead of you accessing it locally, installing it locally, and working with it locally on your computer. Instead, it puts it on a server. So, and then you access it as a client. So it becomes like a client-server interaction, and you don't have to install anything locally. And I believe that this is the best way to approach this introduction to the Jupyter Notebook, because then the transaction cost for you to adopt it is pretty much invisible. All you have to do is point your browser to a website, and then you can access your Jupyter Notebook. Okay. Now, most of you, based on last lecture, most of you have Jupyter Notebooks locally, and based on what I've seen, how many of you have signed up for CHPC accounts, around 7, I believe. I think most of you already have Jupyter Notebooks locally. That's great, and you can work with whichever version of Jupyter Notebook you need to deal with. I thought it would be easier for people to adopt Jupyter Notebook and Python if I remove the transaction cost from in front of you. Now, do not confuse Python, which is the core programming language that we're dealing with. Do not confuse Python with Jupyter Notebook, or Jupyter Hub, which are just a web application that allows you to mix code, text, and Python. This code could be Python or C++ or anything else. Has nothing to do with Python. Do not confuse Python, Jupyter with Anaconda. Anaconda is just the name of a package that is a distribution of Python. You can get Python from different, nobody owns Python, right? There's a standard that the open source community sets for what Python needs to contain in it, but I can develop a prepackaged Python and distribute it. Anaconda just so happens to be one of the most popular data science distributors that has a distribution of Python. And this is the one I typically recommend for you to use, is just go and download Anaconda and the Anaconda distribution. Most of you already have that locally. Those who don't want to deal with it, just access the CHPC Jupyter Notebook. And don't confuse that with Spider or PyCharm, which are just editors that allow you to write Python code and execute that Python code. Spider has nothing to do with the Jupyter Notebook, has nothing to do with Python, it's just an editor. But Spider and PyCharm do not allow you to do the richness, okay, that that I want you to experience when using the Jupyter Notebooks, okay? Now, for those of you who have experience with Jupyter, that's great. For those of you who are new and are probably using the ondemand.chpc.utah.edu, I want you to point your browser. You probably have to, you've probably already have signed up for accounts. So I want you to just click on the link now and go and open up to ondemand.chpc.utah.edu. I will do this with you. Give me a second. So I'm going to open up my browser. I'm going to do ondemand.chpc.utah.edu, and I will share my browser in a second. Okay. So if you point to ondemand.chpc.utah.edu, so you can see my browser link over there, ondemand.chpc.utah.edu and dashboard. Okay, so this website has a bunch of applications provided by the Center for High Performance Computing for you to access a bunch of applications. You know, there's MATLAB, there's ANSYS, there used to be COMSOL, whatever. What we care about is the Jupyter Notebook over here, okay? So for those of you using the on-demand, is this what you're seeing? It would be great if you are okay turning on your camera so that I can see those of you who are opening up the Jupyter Notebook. If you're getting into trouble, I apologize. I cannot see what's happening on your browser. So do raise your hand or just kind of speak up. For those of you who have local Jupyter Notebooks, you know, you can just chill for a moment. And I'm not going to do anything special right now. Nathan is chilling. Okay. So when you click on the app, the Jupyter Notebook, it sends you to this thing over here. Don't worry about anything here. Scroll to the bottom and click launch. Okay. When you click launch, it will start a session for you. It tells you your session is being queued. Please be patient as your job sits in the queue. The wait time takes a few minutes. Okay, so now my session is on, okay? It's not queuing anymore, it says starting. Okay, might take you a couple more minutes. Connect to Jupyter. Okay. And this is what you see. This is a file system where you store a bunch of things. Okay, over here you see, you know, I have Anaconda, Calera, CHEN 2450, desktop, development for Nancy, Intel, you know, a bunch of things. Don't worry about that. Just go create a new Python 3 notebook, okay? And that is a Jupyter Notebook. Can you guys still hear me? For some reason, my audio got disconnected. Okay, who's not at this page? Who does not see this? You got to speak up. I cannot see you, unfortunately, if you're not seeing this. Okay, who is seeing this? Everyone else should raise their hands, right? Are you all seeing this? Those at least I see on my screen. Allison, David, Brooke, Isabel. Okay, so Richard raised, okay, perfect. Nathan, Evan, okay. Okay, so now you can see this. Now, for those of you who, again, have experience with Jupyter Notebooks, you know, probably this is gonna be boring for you. For those of you who have not seen Jupyter Notebooks yet, check this out. So Jupyter Notebooks consist of cells. And when you open a cell, okay, your cursor is going to be blinking inside it, you know, standing by for you to give it instructions. That's pretty cool, okay? Now, there are two primary cell types in Jupyter Notebooks. There's a code type and there is a text type. Okay, so Sovit has a question. Sovit, speak up. Oh, Sovit, you're saying it's working for you. Never mind. Okay, all right. So there are two cell types in Jupyter Notebooks, the code type and the text type. So if you, in a text type. So let's say I wanna put like some text to introduce what this notebook is about. I can select the cell over here. And if you click here over cell, you see cell type over here. There's code and there is markdown. Markdown is the equivalent of text. So I'm going to convert this cell to a text. Okay, now it's text. Okay, and I can just type in it. Okay, so what I'm going to do, my first notebook. Okay, now if you press Shift and Enter, it will execute the cell and render it. Okay, so if I press Shift Enter, look at that, and turned it into text. Nice looking text. Now I can go back to that cell simply by either clicking on the side of the cell, clicking inside it, or, you know, moving my arrow up and just pressing enter, goes back to that cell. Now to format this cell, there's a cheat sheet that's available in my syllabus on kind of how to format these cells, but I'll show you a little trick here. For a header, all you need is one of these sharp symbols and a space. And look at that. Now it gave me a header, okay, my first notebook. And then under it, I want to say by Professor Tony Saad, Department of Chemical Engineering, go Utes, okay? Okay, so it put it like that, all right? Now, let's suppose that in this cell, I wanna start coding. Now, what I recommend when you see the homework template in this Jupyter notebook, you can essentially put text and describe what you're doing. We'll see a few examples as we go through this lecture. But suppose now I also want to describe the problem that I'm solving over here. So I'm gonna convert this cell to Markdown. You can go cell type, Markdown, or as you are highlighting the cell over here, you can press the letter M on your keyboard. It converts it to Markdown, okay? To switch back to a code cell, you press the letter Y. Now you see, when I switch back and forth, you see the difference. There is, when it's a code cell, it shows you in for waiting for input, for coding input. When I switch it to Markdown, it removes that in, okay? So I'm gonna do here, problem 1. In this problem, we will be solving Newton's second law given by the formula, okay? So now I'm gonna put in some math, okay? Given by the formula, F equal mass times acceleration, okay? Now look at that. Convert it to math, okay? Right? We will also solve, I'm gonna show you a little bit more of a complicated equation, the ordinary differential equation given by, I'm gonna put a little bit more advanced math, and we will talk about this syntax. You'll talk about the syntax in your help sessions. This is LaTeX syntax, okay? And you know, as we go through the course, you will learn this kind of by picking it up from you know, translators or other websites, and we're going to be talking about it. But you know, you don't have to use LaTeX if you want to write equations. But if you're like me and you like to see beautifully rendered equations, you better use LaTeX. So here's what I'm going to do. I'm going to do partial, well, for d u by dt is equal to some function of u, okay? Now look at that. Beautiful math for free, okay? Now, over here, you can start your coding, okay? Let's say we wanna plot something, and we'll go over some syntax for Python in a minute, but I just wanna illustrate to you the power of the Jupyter Notebook. I'm gonna import NumPy as NP, you'll learn this, import matplotlib.pyplot as plt. I'm gonna put x equal mp.linspace from 0 to 10. What function do you wanna plot? All right, let's say mp.signx. Then we're gonna do plt.show. Look at that. Isn't this cool? Now you can tell me in your homework, you can say in the plot just rendered above, we observe that the function is oscillatory in nature. We therefore conclude, you know, that this event is periodic in nature, you know, that's it. And that's problem 1, for example, okay? That is the power of the Jupyter Notebook. Now, you can see more advanced Jupyter Notebooks. You can get really fancy with your Jupyter Notebooks. I can point you to, I will actually point you to a bunch of other notebooks that you can find on one of my other websites. One moment, please. Okay, let me, so I can just kind of share it with you. Okay, so if you go to my GitHub, something called GitHub repository, and let's say, you know, I want to show you a little bit fancier notebooks. So you can see kind of how cool you can get with these notebooks. Look at this. I have a full discussion with a full document that I can share with colleagues and friends, and they can get it and they can execute the code and they can understand it and study it. There's usually plots here, but this doesn't render the plots. But this is the level of quality that I am hoping you will be able to accomplish by the end of the semester, okay? This is not for me, guys. This is gonna be for you. The better the product you produce, the more people you're gonna make happy, the more problems you're gonna solve, potentially the more impact you're gonna have, and you're probably gonna be of more value for the company you're working for. Imagine you're running a company and you get an employee who gives you like these beautifully formatted notebooks with a detailed analysis. You're the boss, right? And you're like, wow, this is great. This is what I want. So this is how everyone feels about everyone else, right? So I'm hoping that this is the quality that you'll be able to accomplish by the end of the semester and as you move on into your other courses. Now, I had a couple of naysayers last time in class who did not like Jupyter notebooks. I don't remember. You're sitting to my right-hand side of the class. So I hope you're changing your mind. If you're here, please do share. Okay, so I have some questions on chat. Okay. To include audio and screen sharing, yes. So I can't keep up with the chat because there's like so many screens in front of me, and when I'm sharing, I don't see the chat. So I would rather just kind of interject if you want to say something. That's the problem with Zoom. It's kind of annoying. So I see a few things on the chat over here. Yes, Richard is suggesting change the Zoom setting to include audio with screen sharing. Thank you. Richard is the equivalent of Google now, because when I Googled it, I found that same answer. And so I should have asked Richard. Maybe I'll ask you next time, Richard, help you with technical stuff. All right, so we got Jupyter. Okay, all right. So let's go back to the slides. And that last slide that I had was essentially just a link to my CamPy GitHub repository. Okay, so this CamPy thing is a repository of Jupyter notebooks that I have created for you to study and learn. It has two parts in it. One of them is an introduction to Python and how to use Python. That is going to be your first assignment for you to go through those slides. It's a set of slides. You go through them. I'll show them to you in a minute. And the other one is a bunch of examples in numerical methods, okay? So this completes this set of slides. Let me show you what you can find here on github.com/tony/campy. Again, these slides are available for you on Canvas, okay? And I hope you're following on those slides or just kind of look them up after class, okay? So I'm gonna switch back again to the browser. And if you go to, let me share, okay. Okay, so this is CamPy. If you go to CamPy, if you follow that link, this is what you will see. CamPy, this repository contains Python notebooks from the Chemical Engineering Department of the University of Utah. The purpose of these notebooks is to aid, teach, and educate about Python. There are two notebooks in this repository. There's one called EasyPy and one called Exemplify. I'm like, we're running out of using pi, and people with Python, they're obsessed with adding pi to everything, you know, NumPy, SciPy, Exemplipy, EasyPy, whatever, right? So it's gonna, it becomes cheesy in the end, but still it's fun to come up with names that have Python in them. So Exemplipy, it's a bunch of examples for using numerical methods, like, you know, some examples, how to solve an ODE, how to use lists, how to use NumPy arrays, how to do interpolation. But the important one that you're going to be dealing with in your first assignment is this one called EasyPy. It contains an easy introduction to Python, and you can click here to essentially just access your slideshow in the browser. So this slideshow that you're going to see, that you're seeing right now, has been built using Jupyter Notebooks. So you can even convert a Jupyter Notebook into a slideshow. See the power of the notebook. Now, I'm not going to ask that of you, but that's something you can also work with. So suppose you're doing everything in Jupyter Notebooks, you'll kind of buy into the Jupyter Notebook craze, and you're all into Jupyter Notebooks. You do all your work, all your research, all your studies, or all your calculations in Jupyter Notebooks. You can also pick up your results, convert them into a slideshow in a Jupyter Notebook, and share it with the world, okay? So what you're gonna see here with this Easy Python is, you see this right arrow over here, these arrows, these are your navigation arrows. And you can use the arrows on your keyboard, forward, back, up and down, to navigate this, okay? This is just an easy guide for learning Python. I'm not gonna go through it with you because again, this focus here is not gonna be on programming. And I'm hoping you'll just pick this up along the way, but this introduces you to the programming language and my philosophy about programming. So what you're seeing in this text here is everything I've discussed with you already in class, but I want to get to kind of the first few examples of what you can do with Python. So it introduces variables, for example, for you. So the way you would use this is you open up a Jupyter Notebook in a tab in your browser, okay? I don't know if you remember, there was a time and day where browsers only had one tab, and then Firefox came in and invented the tab system, but all other browsers before even Chrome existed, they just used to be a page, right? So Internet Explorer and Safari, they just used to be a page. And if you want to open up multiple links, you would have like these thousands of pages that are kind of cluttering your desktop. But now open up another tab, okay, and follow through, either put them side to side or next to each other, and follow through these examples that I'm showing you here. You know, how to declare variables, what strings are, et cetera, how to add strings, for example, and, you know, a bunch of other things, what are lists, what are arrays, and all of that stuff. So it should take you about an hour or 2 hours to go through the entire set of slides and to do it side by side. This approach to programming is not ideal, however, because I think the only way you learn programming is when you are actually solving a problem. So when you learn, oh, this is how I declare a variable, this is how I print, but then what do you do with that? You need actual needs, actual example to work with this, to work with programming. So that's why I limited this discussion to only the very, very basics, because you need to start somewhere. You need to start saying, okay, how do I declare a variable? How do I do a for loop? How do I declare an array? And then we're just going to use those in complex manners to solve actual problems. But these sets of slides only contain the basics. And so, you know, if you're new to Python, if you're coming from MATLAB, these will be very helpful, I hope, for you. Okay. And with that, I will end my discussion on Python, and we can get started on our second discussion. Before I go, before I switch, I'm gonna ask the question I hate the most, which is, does anyone have any questions? It's terrible to ask someone if they have any questions, because you kind of put people on the spot. It's weird, but that's what happens over Zoom. You know, when we are in person, I'm like floating around, and I come just start chatting with you, and I ask you questions. And so maybe I'll say, is anyone having concerns about this? Okay. All right. Okay. So let's go ahead and switch up. If you want to take a 1 minute, break, get some water. I'm gonna get some water. Give yourself a minute while I put my other slides on. Let me see this. Okay. Okay. And I need to share my other screen. And I'm gonna make sure I'll share the sound. Okay. All right. Again, if you are okay turning on your camera, I would love to see you and associate your name with you, so I get to know you throughout the semester and the years. But you don't have to. It's not a requirement, okay? You're not required to do that. All right. Okay. So if we are back, let's get started on our first chapter in numerical methods. And I will start it with a motivating example. And again, please give me thumbs up if you can hear the audio, okay?
It's the 4th of June, 1996, and the European Space Agency is launching its brand new Ariane 5 rocket for the first time. This is a big deal. The Ariane 5 is designed to carry large, expensive scientific and commercial payloads into space and heralds a brand new era for the ESA. A decade of design and testing and billions of euros have led up to this day. The Ariane 5 rocket carries no astronauts. The first payload is 4 very expensive scientific satellites to be delivered into orbit. Things start well. The rocket clears the tower and accelerates smoothly. And then the rocket abruptly changes direction, starts to break apart, and suddenly explodes. Less than a minute after launch, huge chunks and glowing fragments of Ariane Flight 501 rain down over the launch area. A shocking disaster for Ariane and the ESA. The cause? A simple, utterly avoidable coding bug. Okay, here's what happened. The Ariane 5 leaves the launch pad and accelerates smoothly into the sky, following its predetermined path towards space. Inside, the onboard guidance system is constantly tracking the rocket's trajectory and sending the data over to the main flight computer. To do so, the guidance system converts the velocity readings from 64-bit floating point to 16-bit integer. Okay, stop for a second and let's think about what that actually means. Computers store numbers in a variety of ways. Consider 4-bit integers. 4 bits can represent anything from 0 to 15. But if you want to represent the number 16, well, there just aren't enough bits, are there? 16's too big. You need more bits to store bigger integers. With 16 bits, you can store anything from 0 to 65,535. Or, if you throw in a sign, then 16-bit signed integers cover everything from minus 32,768 to positive 32,767. But anything bigger than that, and again, you've run out of bits. Floating point numbers are stored a bit differently. They're stored as a decimal, or significand, and an exponent. The details aren't really important here. All you need to know is that 64-bit floating point can store much larger numbers than can fit into a 16-bit integer. So converting between them can be tricky when the integer runs out of bits. So what does happen when you run out of bits? Well, if you're using 16-bit signed integers, the conversion will just wrap around to the beginning again. But whatever the details, you're definitely getting the wrong answer. And this is known as an integer overflow. Right, so back to our rocket. The guidance system reads the horizontal velocity data of the rocket as 64-bit floating point and tries to convert that into a 16-bit integer to send over to the main flight computer. But at that moment, the velocity reading is actually larger than the largest possible 16-bit integer. The system tries to do the conversion and fails. Now, a clever system would have some procedure built in that says, hang on, we're piloting a rocket here. I need to say something sensible to the main computer. It would have some overflow error handling code. But in this case, the guidance system code isn't very clever. so it just sends an error message in place of the velocity data and promptly shuts down. Fortunately, there's a backup guidance system in case the primary module breaks down. Unfortunately, it's running the same code, so it does the same conversion, gets the same overflow, and crashes for the same reason. The main computer receives the error message, and because there's no handling code built in, the computer interprets the message as real navigational data and immediately freaks out. The velocity reading is off the charts, indicating that the rocket is dangerously, impossibly off course. So the flight computer does what it's designed to do. It fires up the boosters and drags the rocket around in an attempt to rescue itself from a non-existent disaster. This puts the fuselage under incredible aerodynamic strain, which starts tearing the rocket apart. Detecting that things are now really going badly, the computer calls it a day and triggers the built-in self-destruct mechanism. So, what was the ultimate cause of this incredibly expensive, very short, and ultimately catastrophic rocket flight? A simple line of code, converting a floating point to an integer that led to an overflow, passed without warning to the main computer, which was interpreted as real, if wildly inaccurate, data. The flight software had been used previously with no problems on many flights of the smaller Ariane 4 rockets, but the Ariane 5 was designed to fly faster than anyone planned for when the software was originally written, and the higher velocity led to the overflow error, a flaw that should have been found, it just never came up. Want to know the worst bit? That buggy bit of code wasn't even necessary during flight. It was part of the launch pad alignment process and shouldn't have been running after liftoff. But sometimes, a small glitch somewhere causes a launch to be delayed by a few seconds. So to save having to reset the system, the original programmers decided to keep that bit of code running for 40 seconds after the scheduled liftoff time.
All right. That is so unfortunate. There are two types of errors committed here in this disaster. Do you know what they are? There's the obvious one, which was the conversion from floating point to integer, which we will talk about. That's called round-off error. Okay, Trayton?
Human error?
Yes, good job. So that's the other type of error, it's a human error, right? The programmers who made that error. I mean, it's a terrible error, and it's always bad when you're converting between numbers. We will learn about that. We don't have to worry about that, thankfully, because we're always dealing with like 64-bit floating point. But that's something you should keep in mind, okay? We will discuss round-off error, which is what caused this disaster, the conversion from floating point to integer, but we will discuss many other errors. So the topic of this chapter is gonna be on errors. And it seems since we're dealing with numerical methods, we're looking at approximations and things like that. Can you guys hear me okay? I feel like my microphone is switching to, okay. You can hear me okay now? Okay. So it seems natural to talk about errors, okay? Because we're doing numerical methods, and you think with numerical methods, you're approximating things. So we might as well we have to discuss errors one way or another, okay? And that is what we're gonna do in this chapter. In each chapter, in each section, you're gonna see a set of learning objectives, which I hope, you will accomplish by the end of said chapter. So I will go ahead and list them just kind of blindly. At the end of this chapter, you'll be able to define and calculate true error, relative true error, approximate error, relative approximate error, identify when a true error and when an approximate error is needed, identify when a relative error is needed, list the common errors encountered in numerical analysis, which are going to be round-off, truncation, and iteration errors, and identify which type of error is present or dominant in a particular calculation. That is going to go throughout the entire semester. So when we're doing iterative solvers, when we're doing interpolation, I'll ask you the question, what type of error is present there? And you'll be able to say, oh, this is round off, this is truncation, or this is iteration error. And finally, write a Python code that computes the Taylor series to a desired tolerance. We're going to do this together because this is kind of introductory introductory chapter. We're just barely touching on programming. Okay, we will start with the definition of true error, and I'll just go ahead and list the definition. True error, also called absolute true error, is simply defined as the difference between a true value of something, true quantity, and its approximate value. We define this with the symbol capital E subscript T. Okay, so capital E for error. This is a kind of the non-relative error, as opposed to the relative we're defined with an epsilon, but capital E is the error, and lower is the subscript T for true. So true value minus approximate value. And oftentimes we report the absolute value of the true error. So typically you're not concerned about the sign of the error, whether you're above or below. What matters is the magnitude of that error, correct? Okay, so we take an absolute value. You use your own judgment in certain situations, which I cannot predict. You might want to have a signed error saying, oh, we are below, you know, the expected value or above the expected value. So you want a signed error. More often than not, you only care about the magnitude of the error you're committing. Okay, our next question is going to be an activity for you. Should probably last a minute or more, but I want you to do the following. So the first derivative of a function can be approximated as fx plus h minus f of x over h, where h is some small value. So that's the definition of the derivative that you learned in high school. So rise over run, correct? So f of x plus h minus f of x over h. H is some small value. Now take the function 2 times exponential to the 0.5x and find the true error in evaluating f prime of 3 using h equals 0.5 and h equals 0.05. Go ahead, grab your pen and paper, your calculators, whatever, and get crunching. Okay, I'll give you about a minute. You're probably not going to finish the whole thing in a minute, but just get started on it. And at least think about what your plan is to calculate that true error, okay? I'll put a timer here on my phone. And if you so happen to be sitting in a study room like Tata, Lexi, Hayden, and who else? I can't read all the names. Feel free to work together on this. Okay, I lost that group. So if you have a colleague next to you, just go ahead and work together as a group on this. I'll give you another 60 seconds. If you have an answer, go ahead and speak up. Hello? All right, let's see. Anyone have an answer? All right, time. Okay. Let's see, do I have any takers on where we get started solving this? Okay. Go ahead, Trayton.
Do you want me to give the do you want me to give the answer?
Sure, or describe kind of what you did.
Okay, so I just followed the formula, and for the for H is 0.5, I got negative 0.609 is the error. And then for 0.05, I got negative 0.0565.
Okay, so let's see what I got. First, does anyone else agree or disagree with Trayton's answers? If you got your answer. Okay, so Max is nodding his head. I can barely see you. Okay, so looks like Trayton might have gotten it right. Let's see my answers on the slides. Okay, so clearly to compute the true error, you need the true value. And where do you get the true value? You get it from the true derivative, right? So, we have the function 2e to the 0.5x, and then you compute f prime, which is e to the 0.5x, and then you evaluate it at the point x equal 3. So that's f prime of 3 equal, e to the 0.5 times 3, which is 4.48. And the next step is to calculate the numerical approximation. And so so the true value is this 4.48. And for the approximation of the derivative, x plus h minus f of x over h. And then the approximate value for the h equals 0.5 is simply you plug into the formula, you get 5.09165. And then the difference is 0.6099. Is that what you got, Trayton?
Yes.
Yes, yeah. So I took the absolute value. Trayton did not, and that's fine. Okay. So you see how we did this. We took the exact f prime at 3 minus the approximate value of f prime at 3. For h equals 0.5, you do the same thing. For h equal 0.05, you just plug in h into the formula. You run the calculation and you get 0.0565, okay? So now when you compare the two, there's clearly, you could say, well, the true error that we committed in using the 0.05 h was much smaller than the error we committed when using the h equals 0.5. But that doesn't really tell us the scale of the error. It doesn't tell us how large the error is, because I could keep that h.5, h 0.05 and choose another function, and you're going to get completely different errors, clearly because the function values are different. And in a way, we haven't kind of scaled the error. So we don't know how big the error is and how much smaller the error is when we went to 0.05 h versus 0.5. So we don't know their relative sizes, right? So that's why a 1 foot error in measuring a 1,000 foot bridge is insignificant compared to a 1 foot error when measuring a 10 foot table, right? So think about it. If I tell you, oh, we measured this bridge, it's 1,000 feet long and our error is about 1 foot, right? Versus, committing a 1 foot error measuring your barn door, for example, or like, you're building a 10 foot table, that's a huge deal, right? That's a huge deal because in the former case, when measuring the bridge, your error is 0.1% of the actual length of the bridge, which is nothing. 0.1% is nothing, okay, by all practical standards. But in the second case, when measuring the table, a 1 foot error in measuring a 10 foot table is a 10% error. That's huge, okay? I'll show you this picture later. This was my setup a few years ago with the green screen, but I'll show that to you later, okay? So that's why we define relative true error. And simply, we take the absolute true error that we measured, which is true error minus true value minus approximate value, and we scale it by the true value. So we define the relative true error defined here by an epsilon. So you notice the capital E is for the absolute true error, and the epsilon T is the relative true error. It simply is the true value minus approximate value, and we scale it by the true value. So that gives us a sense of scale when we are calculating an error. Now, typically, relative errors are reported as percentages, okay? So like I just said, the 1 foot error in a 1,000 foot bridge, that's a 0.1% error, right? Kind of makes sense, 0.1%, normalize everything to a percentage, right? And we also take the absolute value, okay? So if on the exam you're confused, I will be telling you, hey, compute the absolute value of the relative true error, okay? Now, if you were to choose, if I ask you choose, some kind of error to compute, I would, use your own judgment, but I would always take an absolute value and report it as a percentage, okay? All right. So now, here's another activity. Take 1 minute. A 1 meter error is committed in measuring a 100 meter bridge and a 10 meter bridge suspension. Which of those errors is worse? Explain. So you got 1 minute. I know these examples might seem very simple enough. It's gonna get harder, okay? So. Let me put my timer. So a 1 meter error is committed in measuring a 100 meter bridge, and the 1 meter error is committed in measuring a 10 meter suspension. Which of those errors is worse? Explain. That's your question. All right, Nathan's got his hand raised. Do you want to take over, Nathan?
Yeah, it seems pretty straightforward that 10 meter bridge suspension will have a 10% relative true error, whereas the 100 meter bridge will only have a 1%. So the 10 meter bridge is much worse.
Yeah, absolutely. Whereas if you were to just kind of evaluate the absolute true error, you're not necessarily going to be able to kind of tell exactly what that is. So you cannot compare them to each other necessarily. And, spot on. Yep, good thinking. Okay. Let's, this is the example exactly as Nathan said, convert it to a percentage and then, the conclusion that we just concluded. Okay. So now I'm going to remind you of these formulas. And then I'm going to make the statement that true error does not make sense at all. And I'll give you a minute to think about why that is the case. Why does true error, whether relative or absolute, does not really make sense? Okay, so we got Max and 9. I think Nathan left his hand raised. We'll give a turn to someone else this time. Okay, Max, let's just give everyone else some time. Think about what the true error is measuring. And think about what you're doing in numerical methods or any of your kind of engineering measurements and things like that. Those errors, the true errors, when you say true error, what are you after in a numerical method? Okay, time. Let's see. We got Max. I'm ready to answer. Any other takers? Okay, Max, you want to take it?
Yeah.
Go.
So basically, if oftentimes the true error will not have any context to like kind of give it by. Like, for example, if you have a 1 meter error, that could be really good if it's measuring like a 5 kilometer long bridge or something, but it could be really bad if you're going to measure like something that's in a size of 1 millimeter. So the problem with true error is that it doesn't give you what that error is relative to what you're doing.
Okay, so I was after something else, but what you said is essentially putting the true error in context of your measurement apparatus. But suppose you can measure something at the micro scale, and we have devices that measure very accurately at the micro scale. There's another problem with true error. Trayton, I know you got your hand raised, but you already took 2 answers. So let's give the chance to someone else. Kimball?
If you know the true error, you know the right answer. So if you know the right answer, why are you looking for the approximation?
Exactly. Kind of just makes sense, right? Like we are after the true value. But if you know the true value,
couldn't this also help calibrate your instruments? Okay,
so hold on to that thought, Brooke. One moment, okay? But yes, that's going to be the next comment we're going to make. But what Kimball is saying is that, well, if you know the true value of something, you don't need an approximate value. Why are you worried about that? You know, there's no need for a true error, right? Because you would know the true value. However, this is where Brooke's comment comes in. Brooke, do you want to say?
So in chemistry, we work on the micro scale, and I've actually calibrated my instruments in like quantitative analysis and analytical methods. And it's really important to see how far off your instrument is. And like my partners and everyone else in the class had different errors, even though we're using the same instruments. Mm-hmm. And like even, I guess like the clock and all of that is calibrated. And it comes into play too, like in law, someone asks, you know, in a car crash, the airbags will say how fast you're speeding, and how do you know we can trust that number? And it's like, you know, the manufacturers all calibrate these numbers so that you know the instruments are working. Spot on, beautifully said. So to put it in my own words, and correct me, Brooke, if I did not do truth to your comment. What Brooke is saying is that, well, we still need, although if we know the true value, there's no need to go after an approximate value. But sometimes when you are developing a new instrument, a new method, a new numerical method, how do you make sure that your method and your instrument actually works? So you want to test it against things for which we know the true value. That allows us to measure our sensitivity in the instrument, our sensitivity in the method we've developed, how well does it work for problems for which we know the true answer, to kind of calibrate our methods and fix any bugs, for example. In experimental work, this is called calibration. This is called, adjustment. In numerical methods and computing, this is called verification and validation. Okay, Brooke, is this fair? Yes, that's good.
Yes. Okay, thank you. And so we still need the true value when we are calibrating. I like that. I'm going to use the word calibrating. I've been using kind of validating numerical methods, but I think calibrating resonates more with people in general, because validation and verification is not necessarily a word that everyone knows. But typically we use the true error when we are developing new numerical methods and we want to calibrate them. We want to make sure that they work. So we test them on problems for which we know the answer. And this is exactly what we just did. Okay, we took an approximation for the derivative, which is a formula that we came up with, and we want to study how well that formula works. So we tested on a problem for which we know the answer.
And then when we say, okay, you know, on the problems for which we know the answer, for which we know the true value, this is how the method behaves. We fixed a few things. Then now we can take it to problems for which we don't know the true value. Okay, for which we don't know the true value. All right, that's pretty fun discussion, I think. Okay, so in practice, we don't know the true value. Okay, like I said, and yet when we develop our methods, we test them on problems for which we know the true value. So for example, in the next few weeks, you're going to be asked to write a code, for example, to solve a certain linear system of equations called the Thomas algorithm. The first thing you will need to do is check your function on a problem for which you know the answer, because your function better give you the correct answer, the identical answer, okay? Otherwise, you go back to the drawing board before you go and start solving big problems. So I would test the Thomas algorithm, which you will learn about. It's a method to solve linear systems. I would test it on a 3x3 matrix or a 4x4 matrix for which I know the true answer. And then I would take it for a problem that's 1,000 equations by 1,000 unknowns, or 100,000 equations by 100,000 unknowns, okay? That makes sense. However, once you do this, you get an idea of how your method works. Then you go and take it and apply it in the real world. You apply it to new problems. And focusing back on numerical methods, you apply it to new problems. But how do you measure the error? How do you get a sense of how well you've done on that particular problem that you are solving? Okay. So what we do in that case, we define something called approximate error. Okay. So suppose again, now you have a method that you verified and validated with the true error on a problem, or you know the true answer. Now you're taking it into the real world, okay? And you're testing it on real problems. How do you measure, how do you get a sense of how well your method, your device, your tool is doing, okay? We define the approximate error, and we define two errors as well, an absolute one and a relative one, an absolute approximate error and a relative approximate error. So we start with the absolute approximate error, and we define it as the error between a current approximation and a previous approximation, okay? Now, why do I say current versus previous? Because you will often see in numerical methods or in iterative methods, as you are converging to an answer, your latest approximation by construction is closer to the true value than the one before it. So what you do, you take that difference as a measure of error, of how well your method is doing in the real world, okay? Alternatively, so this is an example, vast majority that I just mentioned. So for example, evaluation of many functions, they require the repeated addition of terms, for example, in a Taylor series. And we know every term you add in a Taylor series, I'm assuming you've learned Taylor series. And so I'm going off that. So Taylor series are used to represent realistic functions, complex functions. And the way your calculator works, it just adds up a bunch of terms in a Taylor series to approximate complex functions like sine, cosine, exponential, logarithms, et cetera, and so on. So for example, these are the Taylor series for sine and exponential. They're just simply for sine, it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so on. The exponential is 1 plus x squared over 2 plus x cubed and so on and so forth. So typically in practice, we use this Taylor series to represent those functions, okay? So now you could imagine that, well, you would think that the more terms you add, you have a better approximation, right? For the exponential, the sine, and all of these functions, right? So let's actually prove this, okay? So I'll give you 3 minutes to do this by hand. Use the Taylor series for the exponential to evaluate the exponential function at x equal 2. So your objective is to calculate e to the power 2, okay? Using the Taylor series, however, don't use the true value, use the Taylor series, and use 1, 2, 3, and 4 terms from the Taylor series. So with one term, your approximation is 1, 2 terms is 1 plus x, 3 terms 1 plus x squared over 2. So keep adding terms. And for each one, report your absolute approximate error. So current approximation minus
previous approximation. Okay, you got 3 minutes. And I will say something following up on Brooks' comment. So this would be the equivalent of comparing your instrument or your measurement with your instrument to a measurement with an instrument that is known to have a higher accuracy, higher precision. So when measuring air pollution, for example, there are these low-cost sensors, and there are research-grade sensors. One of them costs $100, the other one costs $10,000, right? So we typically measure the difference between these two, one that gives us a better approximation and one that gives us a slightly less better approximation. So that could give us an approximate sense of the error that is being committed, okay? Looks like half the class disappeared. You have about a minute left. So if you have an answer, just go ahead and raise your hand. And you can listen into your answer. Share my slides with you too. The objective of these activities is to get you crunching some numbers, get you moving, wake you up, you know, see kind of all details. I highly recommend you repeat these exercises before exams and kind of at home after the lecture as you are reviewing these lectures, okay? All right, let's call it time. Okay. So here's what I got in the interest of time, because I probably want to keep you for 1 or 2 more minutes if that's okay with you. So what I got with the one term, the result is 1, but I don't have an error defined for the first term, right? Because that's the only approximation I have. I don't have any previous approximation. So the error could be anything. So there's no error I'm defining here, okay? But then when I include 2 terms, I get 1 plus 2. So that's 1 plus x, right, equal 3. And then I take the difference between the current approximation, which is 3, minus 1. Okay, so that gives me an absolute approximate error equal to 2. Okay, whatever that means. Then we add 1 more term. So we get 1 plus x squared over 2. So that's 3 plus 4 over 2. That's equal to 5. And then you subtract to do the absolute approximate error. 5 minus 3 is 2. So you get 2 as well. And with 4 terms, you do the same thing. You add the x cubed term. And you can see that this absolute approximate error is decreasing indeed, because the Taylor series is a convergent series. More terms you add, the more accuracy you're going to get. Okay. All right. So the approximate error can also be defined as the difference between a more accurate approximation and a less accurate one. Okay. So for example, if we were to evaluate the derivative using a smaller value of h, like that derivative approximation we discussed about, right? A smaller value of h, we know that's going to give you a better approximation than a higher value of h. So that's how you would do it. A more accurate approximation minus a less accurate one. If you have to leave, I understand. Please follow through the lecture on, follow with the rest of the lecture on the video when I post it. But if you can just stay for 1 more minute, I'm going to go through this example with you. So you don't need to do this activity. I will kind of explain it to you because I want to get to the relative approximate error. Okay, so again, the first derivative is given by this fx approximation to the first derivative is fx plus h minus f of x over h. And h is some small value. We know the smaller the value of h, the better the approximation we have. So the question here is, evaluate f prime of 3 using h equals 0.5, but get me an approximate error using h equals 0.05. Okay, so what you would do, you would evaluate the derivative with 0.05 and treat that as the truth. Okay, and all your other calculations are compared to that truth, to that true value. Okay, so in other words, the solution for 0.5 is f prime equal 5.09, and the solution for h equals 0.05 is f prime equal 4.53 or 4.54. So you treat the more accurate approximation as the true value, and then measure the approximate error with respect to that. Okay, so here I take the difference between the two values I obtained, 5.09 minus 4.538, and I get this value for the error. But again, this absolute approximate error doesn't tell us how large the error is. How big is the error? Okay, we're decreasing the error, but by how much? You know, yeah, the values are changing and we can take their difference, but that doesn't really give us a sense of scale. So what we would simply do is define a relative approximate error, which is simply the current approximation or the higher accurate approximation minus the previous one or the lower one over the higher accurate approximation. So that's how we define the relative approximate error. And you can take absolute value over that, multiply by 100%, so you get a percentage, okay? And you call that epsilon subscript A, okay? With that, I'll let you go. Next Tuesday, we'll continue, we'll do a Python example with Taylor series, and we'll start touching on different types of errors, okay? Thank you so much for your attention. I apologize for having to do this over Zoom today, but thank you for your understanding. And I really appreciate your reporting exposures to me. I've had a few reports. Hopefully, you know, we'll get through this. Seems that Omicron is inoculating everyone. So, all right. Thank you so much.
Dr. Saab.
Thank you. Bye-bye.
Thanks, Professor.
Thank you. All right, I'll hang out if you need to chat or anything.